Hello, today we're going to use triangle proofs to sort of emphasize a couple properties that have been seen in many of the proofs recently, but maybe not been explained to its fullest. And so what I want to do is highlight this property. The basics of the property itself, it's called the partition property. What the partition property is saying is that the whole is equal to the sum of its parts. And we utilize this property in two ways, generally speaking. One being with what we call the segment addition property. And basically what it's saying is that if I have a segment, say AB, with the a middle point somewhere between A and B called X, that AB has to be equal to the sum of AX plus XB. Okay, and then the other part of this would be your angle addition property. And so if I have an angle, let's call it A, B, and C with some ray splitting up, let's call that Y. Basically what the angle addition property would say is that the measure of angle ABC is the sum of its parts, so equals the measure of angle ABY plus the measure of angle YBC. Okay, we haven't officially gone over this with you guys before, other than a video a long time ago, but right at the moment it's beginning to pop up in our proofs, and I wanted to review it before you get too far along in them. And so you're probably wondering why this comes up. And so you have a problem like this, and I look at it and they tell me that AB is perpendicular to BC, so I know that this is a 90-degree angle. DE is perpendicular to EF, so I know that's a 90-degree angle. I know that these lines are parallel to each other, and that AF is congruent to DC. And so if I were just to highlight what they've given me, I would know that this is congruent to this part. I've identified that if lines are parallel, alternate interior angles are congruent. And so as I'm looking at this, one idea on how to prove it, there might be multiple, but one idea on how to prove it might be angle, side. But I don't have the side. I only have a part of the side. And intuitively, you may believe that AC is equal to DF, but we have to justify everything with proof. And so what I'm going to do is I'm going to just focus in on that part of the proof that would allow me to state that AC is congruent to DF. Okay? And what I notice is that they share a segment. So this is shared. That part is shared. So it has to be equal to itself, and so I might use the reflexive property, and I might say that FC, because remember I'd have all this other part of my proof, so I'm kind of starting in the middle of it. FC has got to be equal to CF. And the reason why I'm listing them in different orders is because as I travel down the segment, it goes A to F to C, but as I travel, the corresponding letters A and D would correspond, so it goes D to C to F, so that's why that's there. But it's equal to itself because of the reflexive property. And so once again, the reflexive property shows up, and it's really important in our ability to prove so many different types of problems. So you might want to highlight that and just make sure you really understand what the reflexive property is saying. And then the next thing it could say is the segment addition postulate, which would be that AC is equal to AF plus FC, segment addition property. And I could say it as another time where I would say that DF is equal to DC plus CF, and I'd say segment addition property. Okay. And now, ultimately, what I want to do is I want to prove that AC and DF are congruent or equal. So I want to prove those two pieces are equal. How do I build that up? Well, part of my given, so as a reminder, let me just rewrite this, that your given AF is equal to DC. And then directly beneath it, I know that FC is equal to CF. And so if I were to use the addition property of equality, which is what where I can add equals to equals and maintain equality. So I can actually write the AF plus FC is equal to DC plus CF. And I do that through the addition property of equality. And so if you want this as like a side note, it's basically adding equals to equals remains equal. That's what it's saying. So we can shorten that up and just use the addition property of equality. But right here, I have AF plus FC, which I can substitute in for AC. And I have DC plus CF, but that's DF. And so now I've been able to prove that AC is equal to DF, and that's just substitution. Okay, so ultimately what I hope you understand is how you can put together your argument. And notice it's a few lines long. It doesn't just come directly out. You have to kind of put all the pieces together using the segment addition property, using the additive property of equality, and finally substitution. But eventually I was able to get AC congruent to CF, which allows me ultimately to do the proof using angle side. Okay. But that's not the only way we use this partition property. Another such case would be if you have angles. And so right here I've been given that angle 1 is congruent to angle 2, angle 3 is congruent to angle 4. Okay? And as I'm looking at this, they're overlapping triangles, so that can be somewhat difficult to kind of pull apart. But if I pull this apart, at the moment I know that this angle is congruent to that angle. I know that due to the reflexive property, I have the two base lengths equivalent. And I could use angle side angle if only these two angles were also congruent. But they are. And this is how we're going to put them together. Okay, so again, the highlight is going to be this angle addition property. So that's the thing that we're ultimately going to use. I'm trying to show you the examples of how to use it. And again, you'd have all your givens and your statements. But we're really going to focus in on this middle part. And so as I look at this, I have angle 1 is congruent to angle 2, angle 3 is congruent to angle 4. That was part of the givens. And what I do know is that angle A, B, C is equal to, so the measure of this would be equal to the measure of angle 1 plus the measure of angle 3. I also know, so basically I just wrote it out as this whole entire thing. But I also know that DCB, the measure of angle DCB, is equal to the measure of angle 2 plus the measure of angle 4. And you can see that over here. Drawing the picture separate may help you if you can be very accurate with your drawings. So this would be the angle addition postulate. Okay. Next, what I have to do is prove that these two sums are actually equal to each other. But they gave me that, and we'll just rewrite it up here so we can remember it, is that angle 1 is equal to the measure of angle 2, and the measure of angle 3 is equal to the measure of angle 4. So as I'm going through this, if I were to use the addition property of equality, this will allow me to start with 1 equal to angle 2, but then add in two other equal parts, which is measure of angle 3 is the same as the measure of angle 4. And so these two parts are equal, and these two parts are equal. So I should maintain equality is exactly what I do. And then I can just substitute. So the measure of angle A, B, C is equal to the measure of angle D, C, B, which is just substitution. But ultimately that's what I needed to do, and now I can prove two triangles congruent with angle side angle. Again, what I really wanted you to focus on is this setup and the utilization of the angle addition postulate and the segment addition postulate. Okay, so a lot going on there. Really, really important. You're going to find that you're using those more and more often. Yes, it takes 4 or 5 steps to be able to use them properly, but they're going to help open your world as far as proof is concerned. Okay, thank you.